I got called to a water treatment plant last year that had replaced the same magnetic drive pump 3 times in 8 months. Same model every time. Same failure location every time. The maintenance supervisor was ready to write a formal complaint to the manufacturer. Before I looked at the pump, I walked the suction line. 6 elbows in about 15 feet of pipe. A partially open gate valve sitting right in the suction run. And a section of suction pipe that dropped 2 feet below the pump center line before climbing back up to the inlet. There was an air pocket living in that low point every single time the pump was not running. Every startup was a cavitation event before the impeller ever moved a drop of sodium hypochlorite. The polypropylene impeller face was being destroyed from day one. The pump was not the problem. The suction system was the problem. And nobody had ever calculated NPSHa. That is what this video is about. Let me explain exactly what cavitation is and why it is so destructive in corrosive chemical service. When the absolute pressure at the pump inlet drops below the vapor pressure of the liquid being transferred, the liquid partially vaporizes at the impeller inlet. Vapor bubbles form in that low pressure zone. Those bubbles get carried by the fluid into the higher pressure region of the impeller. When they collapse, each one releases a high-energy microjet that impacts the impeller surface at extreme velocity. In clean water service, that erosion is slow. In sodium hypochlorite service, chemical attack accelerates. So, how do you calculate NPSHa? It equals atmospheric pressure plus static suction, head minus friction, losses minus vapor pressure at operating temperature. Every variable must be evaluated at worst-case conditions. Maximum temperature, minimum tank level, and maximum flow. Now, let me walk through the most common NPSHa killers. First is suction pipe diameter matched to the pump inlet. Velocity increases, friction losses rise, and available head drops. Upsizing one pipe size significantly improves NPSHa. Second is low point traps. Any drop below pump centerline creates an air pocket. Each startup pulls that air through the impeller, causing cavitation. This is solved by maintaining a continuous upward slope to the pump inlet. Third is reduced port valves. Gate valves and reduced port ball valves add friction losses. A partially closed valve can eliminate your entire NPSHa margin. Always use full port valves and never throttle on the suction side. Fourth is multiple elbows. Each elbow adds pressure drop. 6 elbows in a short run can destroy NPSHa margin. If the suction routing looks complex, you likely have a friction loss issue. Fifth is fluid temperature. Vapor pressure rises with temperature. Sodium hypochlorite in a hot environment has much higher vapor pressure. If NPSHa was not recalculated for summer conditions, the system may be operating below NPSHa. Now, material selection. The pump, in this case, was polypropylene handling 12.5% sodium hypochlorite at 95 degrees Fahrenheit. That is near the upper limit of polypropylene compatibility. PVDF is the correct material for that duty. PVDF maintains strength and stability in aggressive chemical environments. While it costs more upfront, replacing a pump multiple times per year costs far more than proper specification. Here is the solution we implemented. We rerouted the suction line to eliminate the low point. We replaced the gate valve with a full port ball valve. We upsized the suction piping. We recalculated NPSHa at worst case conditions. It exceeded NPSHr by 4.2 feet. We specified a PVDF pump and added a power monitor to protect against dry run and abnormal conditions. That pump has now run for 14 months without a single service event. Same pump family, completely different result. Because the real problem was fixed. The power monitor protects against 3 failure modes. First, dry run protection. When liquid is lost, motor power drops and the system shuts down before damage occurs. Second, decoupling protection. If torque exceeds limits, the magnetic coupling slips. Power drops instantly. The monitor shuts down the motor and protects the containment barrier. Third, deadhead protection. If discharge is closed, power resets, the monitor detects this and shuts the system down before internal damage occurs. Here is what happens in repeat failures. The pump is sized for flow only. NPSHa is never calculated. Suction layout is ignored. Pipe sizing is incorrect. Material selection is wrong. Protection systems are skipped. Then the pump gets replaced over and over, and the manufacturer gets blamed. But the real issue is specification, not equipment. The engineering required to prevent this is simple. NPSHa calculation takes minutes. Suction review takes minutes. Material compatibility is a loop cut. The difference is whether someone actually does it before installation. If you calculate at installation conditions, you may show adequate NPSHa, but in real conditions, that number can drop below NPSHr in corrosive service. Liberty CES applies a minimum 3.2 8-foot margin between NPSHr to protect polymer components.